Okay, so let's look at a more challenging example here. Let's look at the integral of e to the x times the sine of x dx. Okay. I don't think it's entirely clear that integration by parts is going to work on this problem. And the reason why is because if I take derivatives or integrals of e to the x, I keep getting e to the x. And if I take derivatives or integrals of sine of x, I keep getting either sine of x or cosine of x, or variations up to a negative sign. So it's not clear that as I apply integration by parts, my problem is going to get any easier to work with. But we're going to go ahead and do so anyway, and we'll see why this works. The other thing I would say is that, unlike my previous example, this is a problem where we have to apply the integration by parts formula more than once, which is a common thing to have to do. So I'm going to go ahead and I'm choosing to let u equal the sine of x. In this case, it actually doesn't matter which one I pick u to be. I could pick it to be the sine of x or e to the x, and either way I'll get through the problem. When I was working it ahead of time, though, I found it was a little bit easier as far as the signs went if I let u be the sine of x and just kept the notation a little clearer. So if u is the sine of x, then a consequence of that is that the derivative of u is the cosine of x dx. If you have any problems about going from this step to this step, please let me know. Then we've got to let differential v equal the other factor times the differential, so e to the x dx. So just to clarify what we've just done here, we said, okay, we'll let u equal the sine of x, there's sine of x, and then we said, then we'll let differential v be these factors multiplied together, e to the x dx. So we're taking care of everything underneath everything within the integral expression. So if differential v is e to the x differential x, if I integrate both sides, notice when we do integration by parts, the u's we differentiate, the dv's we integrate, we get v is just equal to e to the x. So now we're going to follow the formula. So we've got the integral of e to the x times the sine of x dx, that's just the original, is equal to the product of u and v, so sine of x times e to the x, minus the integral of v, that's this factor, e to the x, times du, which is the cosine of x dx. So again, if you're following that formula that we derived before, we had the integral of u dv is equal to uv minus the integral of v du, following that formula based on what we wrote up here. Great. So first of all, I don't think it's clear that we made our problem any easier. This integral does not look any easier to compute than the original, so that's something to keep in mind. But I think that we could apply integration by parts a second time here, and let's do that and just see what happens. So here I've got to stick to my guns. In the previous problem, I let u be the trigonometric term, so I'm going to continue doing so. I'm going to let u equal, and now I'm going to perform integration by parts on just this integral right here. So I'm going to let u equal cosine of x dx, cosine of x dx this time. So, I'm sorry, I'm going to let u equal the cosine of x, just the cosine of x, and then differentiating both sides gives us du is equal to minus the sine of x dx. Differentiating cosine, we get minus sine, and so actually it's worth pausing just a minute. Why do we always write it that way? Really what we're doing is we're saying du dx. If u is equal to cosine x, then du dx would be minus sine of x, and then we sort of formally manipulate the differential symbols by multiplying both sides by differential x, and we get this expression here. So usually people will just eliminate that middle step. And I'll go ahead and do that too now. So sorry to make that run a little long. So we let u be this cosine expression here. So again, let me see here. U is this cosine x dx, right? U equals cosine x, and then there's a consequence there. And then we'll let our differential v be this expression here. So we have differential v is equal to e to the x differential x. Integrating both sides gives us that v is just equal to e to the x. So this is the part where bookkeeping becomes of most importance here. This is why integration by parts problems can get long and tedious, and it's easy to make mistakes. So here was the original problem, the integral of e to the x times the sine of x differential x. We said in our first iteration that that was the product of sine of x e to the x minus, and now I'm going to handle this integral inside of here by again applying the integration by parts formula. So we've again got the product of u and v. In this case it's cosine x e to the x minus the integral of v, which is e to the x, times du, which is minus sine of x differential x. Okay, let me take a line. I'm just going to recopy this line here and clean up the right hand side. Okay, watch your negatives here. I could factor this negative outside the integral, which would then give us a double negative here, and we've got it. So this would become minus the integral of e to the x sine of x dx. So pause it if you want, double check that I did my negatives correctly, but notice we've got these three negatives here that we can combine into a single expression. So this is the point that I wanted to get to. Okay, so I'm trying to solve for this integral here. I'm trying to evaluate this integral, and here I'm actually going to now solve an equation to figure out what that integral has to be. So if we were looking at something like this, it said x is equal to say y plus z plus x, and you wanted to figure out what x is, you could let me make that a minus x. You wanted to figure out what x is, you could go ahead and add this x over to the other side. You'd have 2x equals y plus z, and now you could solve for x. X is equal to y plus z over 2. So I just want to use that as an analogy for what we're doing here. I've got an integral, and I want to figure out how I can represent this antiderivative, but that integral term shows up again over here. So what I'm going to do is I'm actually going to combine these two integrals. So I've got an entire equation here, right? And so I'm going to combine these two integrals into a single term by adding this integral term over to the other side. So that gives us 2 integral e to the x sine of x dx is equal to sine of x e to the x minus cosine of x e to the x. Okay. And now I can go ahead and divide both sides by a half, and we will have isolated the integral that we're trying to solve for. And we can't forget to add that obligatory constant plus c in this technique. Because we never formally evaluated the integral, we never ended up with that plus c. So we actually just have to tack that in, recognizing that that constant needs to be there. So this is a really interesting way of solving an integral. Maybe you remember this from earlier calc classes, but that's an interesting way of evaluating the integral. We never actually evaluated it. We just applied the integration by parts formula twice and found out that we were back at where we started after we applied it twice, essentially. And so we added this integral over, forming a sort of an equation in which instead of solving for x or y or a number, we solved for the integral for which we wanted to know the antiderivative of. This was a little bit longer video. This is certainly a more challenging example. Let me know if you have any questions over this. Bye-bye.